the delay.
So I already did the introduction. So Pedro, if you can just leave like 5 minutes, 10 minutes towards the end for discussion.
Yes, of course. Yes,
Okay.
I think we have time.
I already introduced you and our former affiliations. So please just get going.
Okay, so the topic is load shifting, and the focus is on the dynamics of such shifting when we deal with populations of flexible loads. So this is I chose the topic because not because it is a matured one, but exactly by the opposite reason. I think there is a lot to learn on this subject, and I hope you appreciate this rather exploratory talk about the subject. So the contents, I divide this in 4 chapters, 4 parts. One is the first part is to introduce the model. So the model is very simple, okay, but yet there are lots of complexities that are enclosed by it. I think you will understand what I mean. And then the second part is using the model to understand its main properties, and you will see how the limitations on control somehow emerge directly from that. Then the third part is changing the model from direct control to indirect control. So we'll try to see what happens when we start controlling the shifts of the loads in time based on incentives, based on prices, assuming there is a transparent market clearing process. And then finally, we'll use those results to try to figure out what's the value of vehicle to grid responsive services. And we'll see that apparently there is not much value there from the controllability point of view. So starting with the model. So the model is a particle hooping model. So we will model load particles as we'll model loads that can be shifted as hooping particles. So we'll use them. We will consider that those particles can be shifted ahead in time until they collide with the particle ahead in time. So the idea here, that there is this figure on the right, that and we see that there is a schedule of consumption and in the top figure, and then because there is space between the time for consuming for the first time and the time for consuming for the second time, we can delay the storage period by moving the particle one step ahead in time. Okay, those kind of.
Pedro, excuse me, just a logistic thing. Just what I did on my screen in the view. This is for people who are listening. In view, I think there was a checking which says side-by-side slides. If you just check standard, then you're going to see on the entire screen the slides. If people have the same problem where you had maybe showing something empty and then very little on the slides. I don't know what your situation is, but if you click on view in top on your own, it says standard and side-by-side speaker. You want to uncheck side-by-side speaker and just check standard, and then it shows full slides.
So you are not seeing the whole thing?
No, we are now. This was a problem on my side, I think.
Ah, okay.
Sorry. Can you see? Yeah, perfect. Thank you. Keep going. We figured it out. Yeah.
Okay. So the idea here is to model the shifts like this. So I can shift the loads ahead until there is a time to use that load. So somehow someone stored the load and then is going to use it. Imagine that this is a water heater. So someone heats the water and then it will use the hot water sometime in the future. And when someone uses that hot water, he has to heat it again, right? So I can shift this load particle that corresponds to the consumption to heat the water, I can shift it until the time of use, right? And then after the time of use, there is in the schedule there is another period to store, and then I can move that particle, that second particle again until it collides to the third. This is like this for loads that are water heater loads, but it's also the same for plug-in electric vehicles and some other kind of loads. And these loads are not usually called in the literature as interruptible. Those are a subclass of the what people call curtailable loads. And here we are considering that those are perfectly elastic in the sense there is no loss, no loss of energy, but they are confined in time. So I cannot delay that period forever. I have to use it somehow, somewhere in the future. Okay, so each of those delays in time can be represented by in an array of particles. So let me go back. So you see there is one particle here in time 4, one particle in time 7, and one particle in time 13. I think I don't see it, and then I can represent that here in the first row. One particle in position 4, one particle in position 7, one particle in position 14, I think. Right. So this is for first consumer, the first user. And then if I have multiple users, in this case, I think I have 8. Let me check. Yes, I have 8 users and 17 periods. So I represent each of the users in one row. Okay, so this represents a small population of users that have this kind of elastic loads. So there are 2 dimensions here. One is the user dimension, the vertical, right, and then the time dimension, the timestamp dimension in the horizontal. Okay, so if I shift all the loads the maximum as possible, so if I assume that I have the maximum flexibility, so I change my this first lattice into the second one. You see that particle here can be shifted until here, right? So in the bottom, she becomes placed here, and then the second one, it collides with the second, and the second one can be shifted until here, right? Do you see my mouse?
Yes.
Okay. So the second one is here. So if I shift everything as much as possible, what I can change the aggregate load that corresponds to the sum of those particles within the columns. I can change them from the lattice in the top into the lattice in the bottom. Okay, this is the maximum flexibility, maximum load flexibility I can extract from that population. Okay, so particles. So the idea is particles can be moved ahead to positions unless there is a position that is occupied, right? So the dynamics of shifting can then be modeled as that of multiple elastic collisions in time, right? So there is a collision with one particle with the one that is ahead in time, right? So and now the question seems to be, how can we regulate that? How can we regulate those shifts in order to be able to modulate the aggregate load? So, and we will see that. We will see how we can do that with ideal control. So we'll start by that. Ideal control, in the sense that in the sense that we will have full real-time observability, but no information about the future, just real time. So we will not know to start with what the schedules are for each particle are. So this is private, but we will have real-time observability of the state of the loads. We'll see. Let me show what happens in time. So this is a lattice of, I think, 50 particles or something, 50 users, and what I was what we want to do is to shift. You see the shifts in the top here, and you see the result of the aggregate load in the bottom. So what we want to do is know how to shift in the top in order to try to control the aggregate load of the population. So are you seeing the movie?
Yes.
Okay.
So so this is the aggregator level, Pedro.
Yes, the aggregator level. Yes. So
Okay.
so somehow we are assuming that we have control over each particle, but we don't know what the schedule is. So we are looking at what at a target load for the population and trying to modulate it. We'll see how. The control algorithm is quite simple. So the assumptions here are that we have ICT. So ICT is good enough for us to have time synchronous update of the individual particle shifting decisions, and we also have ICT that is good enough to have a real-time observability of the aggregate value, but we don't have. So we are assuming that privacy does not allow us to have information on what the schedule for each user, schedule of use of the load is. So we don't have that information. And what we want to do is now to follow try to use our control capabilities over those shifts to make the population follow an aggregate load. So we are defining P as the aggregate load, right? So P is the sum of all for all users of their use in time. So D is the use. D is you are using the load or not. So there's a particle there or not, right? And then we are summing those in times. That's P. That's the power that we want to control. And to do that, so and we have a target P star. So P star
excuse me, Pedro. When you say we, that's the aggregator.
Yes, the aggregator. Yes,
okay.
Someone that has
just
control.
To double check, is not the utility, is the aggregator.
It's the aggregator. Yes.
Okay.
So how can we model this? So we can model this with a very simple cellular automaton algorithm that looks at each particle in each time period and sees and compares the sum of all the particles in a given time with the target. And if the sum is above the target, so if I have more particles than the target load, I shift particles ahead. So that reduces the load. So this is very simple from the programming point of view. So we just have to check if there is a particle there. So for each of those users, I just have to check if they are planning to consume at that particular time. So if D is equal to 1, and if there is an empty space ahead. So if I can move the particle ahead. And if so, I just do the opposite. So I change the one for the time ahead, and I change and so it reduces load instantaneously at that point in time, and it increases load in the time in the following time. And if we do that, controlling just to reduce loads, we can ramp up and down quite easily. You'll see that. So the idea now is to see how can we ramp down and ramp up based on just that simple idea, right? The idea of having, if we have a load that is higher than the target, I shift particles ahead. If the load is not higher than the target, I just manage the growing of the load. So we'll see what the insights from simulation are. So we are going to simulate with different ramping rates and see how the model works. So the idea here is to see when when we can do that control with an acceptable accuracy, and when we cannot. So to start, so to set up the case, we need to generate a random set of particles, a lattice of particles. We are assuming that we are doing that. We'll see that this is not a necessary condition, but we are starting by a sample of particles that is random, but has a fixed density. So the number of particles divided by the number of empty spaces is constant for every particle. So we see this is almost, the loads are homogeneous in this sense. And to do that, we generated a very simple Markov process. So we use a Markov process with just one parameter, which is the probability of changing from state 0, which is no load, to state 1, which is a particle, right? So we need just one probability, which is the probability of transitioning from state 0 to state 1. And then once we are in state 1, we change immediately. So there are no two particles ahead, just one. Right. So once we charge, the time ahead is an empty space. So, and by doing that, we define density. Density is the stationary probability of a particle. So based on that probability of changing from 0 to 1, this density can be defined as 1 minus 1 divided by 1 plus that probability. So it is okay. So a couple of definitions now for us to understand the results. So the ramping will be around the average. So because we have an average density, so it's very easy to see what the expected load is if we do nothing, right? So the expected load would be the load if control is not activated. So the average load will be the density multiplied by the number of particles, and then we are going to change ramp up and down, so a triangular wave function around that average, right? So average here in the right hand side, you see that we are ramping up and down. There is a percentage here around 0, because that 0 is the average, right? So we are ramping up and down around the average. This is the result of the control, right? And what is happening? So how do we do that? How do we ramp up and down? We ramp up and down in that accurate manner by managing the shifts of the particles, right? So we are shifting particles in time at a given rate. So the rate of shifting, we call it velocity, right? So the number of particles we change, so the number of particles we shift ahead in each period is called velocity, because this is we designate velocity because it's a measure of the number of shifts per time period, right? So here is velocity in the second plot, right? So we'll see that velocity is the integral of the change, right? So velocity is here, and in the bottom plot is the lattice. So the number of, so I'm putting a dot in each particle that is changing. You see that it looks very much the same, but it's higher. So here I have to change velocity, means that here around time 20, we are shifting 120, something around that particles. But to shift 120 particles, I have to call for shifting. I have to ask for shifting something around 150, because some of them will not be there. So particles will not be there. So I need to call for shifting more particles than the ones that are in fact shift. Okay, so the number of particle shifts, we call it V, right? So it's here, the definition is the number of shiftings in time, right? And then we see that the difference here, the difference in aggregate load will be the difference, that the delta will be the changes in time, the changes in velocity. This is an important concept. So what makes the changes in the loads is not velocity, is the changes in velocity. It will be like an acceleration. Okay, so a little bit more about that. So velocity here, you see. So if we integrate, if we solve the difference equation, the one before, we solve it like this. So this is the equation was, sorry. Oh, it moves ahead. Okay, so this is an ordinary difference equation, right? So the solution is just the sum of the deltas. So velocity is is the integration of the changes I want to make on the aggregate load, right? So if we look at if we want to understand what we can do and what we cannot do with those numbers, with that population of particles with a given density, we have to look at what we can do about velocity, which is the velocity, which is the maximum velocity we can reach with our control. So when ramping down, which is shifting, to make a triangle, to make a ramp up and then ramp down and then ramp up. You see here. So we have to accelerate the shifting and then decelerate, but still increasing the velocity. So maximum velocity is reached in alpha cycle. So after in alpha cycle of that triangular wave, we reach the maximum velocity. This can be seen if we go backwards. You see that maximum velocity here is reached when we complete alpha cycle, right? So, and the ability to complete that alpha cycle without errors in following that target, the capability of doing that is directly related to the capability of reaching that maximum velocity. Okay, this is important because maximum velocity is something that does not depend on the slope of this triangle wave function, but on the area of it. So this maximum velocity is a measure of the magnitude divided by the frequency, not the product. So we would expect something around the product, because we would expect that the difficult targets would be very steep targets, but it is not. So it's the area. So I can increase magnitude if I can increase frequency at the same time, right? So you see here on your right, you see a load following that is not very accurate. So there are errors there because we are reaching. You see here, I'm calling all the particles to move, and they are not enough. So so velocity reaches its maximum. But I can reach the same amplitudes, the same magnitude. You see here, magnitude is 50% of the average. So I'm ramping up and down the average load by -50 and +50, right? It's a lot. But I can do that if I do it faster. So if the slope increases, so if frequency of the wave increases. So if you see there, so I can do it's the same population, and I can ramp up and down accurately, okay? And just because I just reduce frequency. So this is a quite nice result, and this behaves very well. So that relationship is very solid. Another important thing is how the capability to follow load depends on particle density. So if density is very large, it's not the same as density being very small. So one particle in 10 in average is not the same as one particle in 3. So the way the maximum magnitude change for fixed frequency, if we fix the frequency and just look at what we can do regarding magnitude, for a given density, we see that the maximum magnitude is an exponential function of density, negative exponential. So that is reported in 2009 paper.
Pedro, Pedro, at the expense of, I think we can make it interactive. People can ask also.
Yes, of
a
course.
relatively small group. So I encourage people on the chat to ask, but I think at the expense of interrupting too much. I want to ask burning question that's on my mind as you're explaining this. A lot of people from our group on the call, they work in these energy dynamics. I think there is a fascinating interpretation of what you are talking about in terms of, acceleration rate of these velocities actually second derivative of stored energy that you have in these loads. And the question is, what ultimate limits, how are you shaping basically the energy dynamics so that you optimize things? Just the food for thinking for later for us to follow up, but also for people on the call, think about what Pedro is talking about in terms of our energy dynamics modeling. Sorry, just
those are small dynamics in the sense that we are talking about slow changes. So
but it is okay. You can
minutes, hours, half an hour.
You can still think about this the process, quasi-static process. Also, it's energy dynamics evolving at a certain slower rate. And the question is, I think the big point that I heard from you is that it's rate of velocity, which is acceleration, that matters.
Yes.
It's not just the velocity. And
because if you keep changing, if velocity is all the same, you are shifting always the same number of particles. The aggregate load doesn't change. So it's the change in the speed of if the rate of change, it is the rate of shifting that makes the differences.
Yeah, but I think we will follow up with you on that. Is actually
yes.
Thank you. Yeah.
Okay, so this is if we look at the results and do a lot of simulations, what we can abstract from experience are those two relationships. So in one way, there is a max. So the inaccurate responses are expected if magnitude is above that line. Okay, so I am putting magnitude here in frequency. So there is a limit for the maximum that is the rate of magnitude per frequency. And also but now in a logarithmic scale, there is something similar with density. So if density is very small, I can have very large magnitudes. If density starts increasing, I cannot. And this is almost linear in a logarithmic scale. If densities are not very high. If densities are very high, then the collisions are so many that it gets so that we cannot abstract. We can no longer say it is an exponential. Okay, so now the question is, okay, this is direct control, ideal. So what happens if we change from ideal control, direct, with very large band communications, now for something that is more realistic, which is trying to see what we can do with incentives. So if we have a price, if those users bid the price for shifting, and we have control over the prices, what can we do by controlling the prices in regard of the aggregate load? So how can we control aggregate load based on prices, assuming that those users bid the price, right? So one important thing that I didn't mention is that order. The one thing in the dynamics that is critical is that we have to keep shifting the same loads, the ones that we shifted before, right? So there is an implicit order. If we just shift randomly, we do a lousy job. So it's very important to have some kind of priority for shifting. We can see that, and it's very easy to demonstrate, because once you shift a load, that load becomes available to be shifted again, right? So it's easy to use. So the dynamics is there. So once you shift it, she becomes available to be shifted, unless she collides with a particle head. If you are always looking at if you look randomly, you lose that kind of dynamics. So priority is very important, and bidding price implicitly creates a priority. So the changes, we'll see that the changes are not going to be very different between direct control and indirect control, but there are some subtle things that are quite important. So what do we need to do regarding the control algorithm? Very little. So we just have to replace the condition of the load being above the target for a condition which is the price being below the price. So once you offer a price, everybody that has a price that is lower than that will be willing to shift. So from the cell automaton point of view, very small change. Okay, so instead of providing a target for the aggregate load, what we need to provide is a target for the price. So we change the P star, we change from the P to a pi. Okay, and now the question is, can we what we really now have to know how to do, learn how to do, is to come up with the right pi, because one thing is the right P is the natural target. Another thing is the price, which is something that we have to find in order for the P, for the load, to do what we want. So the change is quite simple, changing from P to pi's, right? And as before, the changes in aggregate load that are now necessary to reach the target load are obtained by controlling the velocity. So it's the same. This is exactly the same. What is the difference? The difference is that the price is not a function of the shifting velocity. It's not a direct. It's not a linear function of velocity. And why is that? Wow, right. You can see. So let's first see it is not, right, because you see here. So this is a target triangle, more or less. Sorry, more or less a triangle function. And now you see this is the wave here, which is the number of responsive actions. So this is the lattice. You see the lattice is not really the integral of that one. There is the wave anticipates itself and then it delays. So there is kind of an anticipation and a delay. It's not like before. See, before it was not like that. You see, so those were very much in line with velocity. Now it's not like that, right? So and the reason is that the relationship between the number of shifts, which is velocity, and the number of calls for shifting, right? So how many particles do I need to call in order to get a certain number of shifts? And that changes that, and the price, I think the crux is here. The price is proportional to the number of calls, not to the shifts, right? Because I have to increase the price until they respond, and when they respond, they shift, right? But the price is proportional not to the number of shifts, but to the number of calls for shifting. And the dynamics here, the dynamics that create that kind of wave, are caused by something that is, when we shift a particle, that particle becomes available to be shifted again, right? If you don't call it, then you lose the opportunity to shift it, because it stays behind in time, right? So, and because of that, if we look at the relationship between the number of calls, which is the price on the vertical, so the ordinates, and the velocity, which is the number of shifts, there is an hysteretic behavior here, right? So when when there are no particles, so when I start, particles did not accumulate yet, so I have to call for much more. And when they are in move, I can easily manage, because there are many particles in moving already. I can manage the ones I can manage by regulating the price. How many of them I lose behind, right? So this makes the control based on price much harder than the direct control. So, and this can be, I think, synthesized like this. So when a load is shifted ahead in time, it becomes available to be shifted again. So and because it becomes available, so the price doesn't have to increase much. Once you and before you have a big number of particles to manage, before you have those amount of particles in the move to be managed, you have to call for a higher price, right? So this non-linearity, this is a non-linearity, right? So it's here, time was removed from the equation here. So I'm just plotting velocity against price. So that non-linearity makes the life of those that want to predict what the response is based on price quite difficult. Okay. So this is just an explanation of these traces. So you see there is a price here is in blue. Okay, orange, there is velocity. So velocity is responsible for the change, but price is what you have to call to get that given velocity. So what can we do about this? So we can what we can do is trying to understand, trying to model that behavior. Because if you can model, probably we can use the model to learn how to change the prices in order to get a given result. So indirect control can be approximated so by an equation, so that the change in velocity, so this difference equation on velocity can be written approximately for large enough densities, can be written as a linear equation. So and this is an approximation, but I think it will be good enough. We don't know yet, right? So this is quite exploratory. So, but it might be good enough to learn how to control loads based on prices. Okay, so we have this. So this is the real one from simulation, right? This is the one that is obtained with this linear equation. Okay, so those equations can be used to predict responses and to be able to come up with prices to obtain a given response. So these ordinary difference equations can be used to learn. Okay, because now if I use velocity again, and if I use the previous equation together with the integral of the velocity being the change, I can write the change based on prices. So the equation we have here is an equation that predicts the change on prices, or predicts the change on load based on the sequence of prices. Okay, but that relationship, which is the one we want to learn to be able to control load, so relationship in time, the dynamic relationship between changes in the aggregate load and changes in prices, involves velocity. So velocity is a state variable, and here the idea is that you cannot control loads in a population based on prices if you don't use velocity, if you don't keep track on how many particles you are shifting in time. So otherwise, if you don't do that, it's impossible. So if you want to write a machine learning, if you want to write a machine learning algorithm that uses a time series of loads and a time series of prices to be able to predict loads based on prices, you cannot do that if you don't have a time series if you don't add a time series for velocity. So you need the three. You need loads in one side, or changes in loads. You need prices, an historical time series of prices, and velocity. Otherwise, learning will not be possible. Okay, so now I don't know what time is it. I changed. I have to pick up my clock. I moved.
It's okay. We have time.
Yeah, not many.
No, we have enough time. Don't worry.
Okay, but this is the last one. This is the last bit. So now about V2G. So vehicle to grid responsive service. How can we use what we know, so what we have presented so far, to understand what would be the value from the control, from the load, from the aggregate load point of view, the aggregate load control point of view, what would be the value of V2G? Okay, so we have to start by modeling the discharge of the vehicle, right? Because one thing we call it V1G. V1G stands for the normal shifting, smart charging. This smart charging of the plug-in electric vehicles. So something I can control the time, or at least the starting time. And V2G is the ability to discharge the battery and inject power into the grid, right? So what we can do is we can look at the difference between shifting and discharging. Okay, and so let me just use like 2 minutes to do that. So in the top there are two figures, okay, two plots. One plot is of a particle, which is a shifting. You see, there is a shift. My mouse, okay, there is a shift here. Shifting ahead. Shifting ahead does what? When I shift ahead, I look at what would be the expected. So there is a schedule that would be the average, right? Here in the if I look at the state of load, when I shift ahead, I reduce a bit the load, right? The load is not just the load of that one, it's the load of many, right? So when I shift one particle ahead in time, so I don't charge, and I was expected to charge, there is a depression here, so there is the hole, right? And then there is a potential rise, because if I don't charge here, I have to charge later, right? So but that rise can be shifted again, right? So here I decided I was expected to charge and I don't charge, right? So there is a depression in the expected load, and then there is a rise in the future, right? But that rise in the future, I can decide when, so I can shift that part in time. Okay, this is for the normal thing, so normal shifting. So what happens if I use vehicle to grid? If I use vehicle to grid, first I have to charge, otherwise the battery is empty, right? But once it is charged, I can discharge, but that charge was expected, right? That charge was expected, so no change in the expected load is foreseen, right? But then I decide to discharge. This is the decision. So I decide to discharge, and when I decide to discharge, I create a depression in the aggregate load, right? And so from that point of view, it's very similar to the other one. So the charging, shifting the charge or discharging is exactly the same from the expected load point of view. And what happens next? What happens next is because I discharged my battery, I need to charge it in the future. So again, there's an opportunity. There is a rise in the future, and that rise can be managed in time. So the thing is, what is the difference between the two, right? So they look exactly the same from the control point of view. So one is shifting, the other one is discharging. But once I discharge, I have to charge again. So there is apparently there is no difference from the aggregate load point of view. Okay, apparently, but there is a small difference. Okay, so summarizing, so shifting and vehicle to grid decisions impact on the aggregate load by decreasing the expected load at the time of decision making. So one thing is deciding to shift, another thing is deciding to discharge, but they decrease the load at the decision time. And then what they do is they create an opportunity to shift the load again. So there is a shift in the future. There is an increase in the load in the future, but that increase in the future can be shifted again, right? So the sole difference, and this is an important one, this is I think main difference, is that vehicle to G allows one to decide about when to discharge. So the vehicle to grid, I have the battery is charged already, so I can decide when to discharge. And the shift doesn't, because the shift I have to decide at the time that was planned to charge. So I cannot manage that time. So now from the control point of view, from this very simple cellular automaton algorithm, what are the differences? So the difference is that they are also very small, okay? And the difference is I have to add another else if condition to the decision. So I had something that was just like this. So if the bid was, so if the price for shifting was high enough, so I would change and shifting. I would change my position. So I would delay my charge. This is the traditional stuff, V1G. If I want to make V2G, I had to add an else if condition, which is if it is zero, it's because it's one in the past. So if it is, so the other one was, if the particle was there, then it becomes ahead. So I shift it ahead, right? So that increases velocity, right? V. And now is, if it is zero and it is zero ahead, so I have space ahead. So what I do is it becomes -1. So it's again a depression. But the difference is 1, but the level is 0. So it becomes from 1. Here the change is from 1 to 0. Here the change is from 0 to -1. It's the same quantity, right? And then again in the future it appears a charge, and then I can delay that second charge. So it's very simple. So let us look at the results that we get by simulating that. Okay, so the results. The important thing here is being able to shift loads in the future, and that's my point. So the real value is not the value of discharging, is that when you discharge, you get the opportunity to charge again, and this is the opportunity to charge again from the dynamical point of view is the most important thing, right? So here we have the results of, again, so ramping up and down, okay, and then you see this is the shifting. The red one is the number of shifts, so it's very large compared to the number of discharging, and I am assuming that they go for the same price, which is also unrealistic. If it would be realistic here, the blue one would be negligible. So, and we see on the bottom, we see those are the decisions of shifting, right? So the usual one, V1G decisions, and in the bottom you have the discharge decision, right? So these are the battery discharging decisions. So they appear in the front end, in the front wave of the V1G decisions. So, but what is interesting here is that now we don't have that delay. Now what we find is that the delay is not there. So these hysteresis on the velocity disappeared because of the V2G. So the effect here is not, so this effect is very small of discharge, but because this discharging creates an additional opportunity and in which you have control, that non-linearity in control disappears. So you see the difference. If we wouldn't use the discharge, the wave would look like that. So if we would use V1G alone without V2G, the response would be this one. You see, so there is much more steep here. It goes much higher in the number of calls. Sorry, the number of calls. Here, if we use V2G, you see this is a perfect sign. Okay, and it doesn't go as higher, just because of those small number of V2Gs. This is an interesting result that we can with a very simple model. Okay, so the opportunity, because V2G creates an opportunity. So the opportunity is not there, you create it, because when you discharge, you have to charge again, and because this is something you have control of, on controlling the opportunity, it creates a value, right? And the value is here. So you see that the price, this price you can control. So if you have V2G alone, you get an hysteresis cycle as you did before with the normal with the other loads. And if you have V1G plus V2G, you get a linear curve, a linear relationship between decisions and prices, and that makes the expenditures of the aggregator go down. Okay, so because prices are now lower. So this is interesting, and so this is interesting not just because the price becomes lower, but because the control becomes much simpler. So if you now want to learn how to regulate the prices based on how to regulate the load based on prices, now you have a linear function. So it's much easier. So you don't have to involve velocity now. So you can neglect velocity if you want to learn if you want to learn how to do that. But we are assuming that those goes for the same price, vehicle to grid and delay and shifting, which is not very realistic. Okay, so in summary, okay, because I'm getting slow. So in summary, we propose a model for load shifting, very simple one. It relies on particle hooping models, and despite being very simple, it seems capable of realistically representing the most important limitations. This is interesting, and I think it can be explored. Students might be interested in exploring this, because I think there is room for making many different things around this, changing just removing the assumption of homogeneity, many things that can go around that are quite interesting. We changed the model to respond to prices instead, and found out that control based on price is subject to important supply dynamics, and this is interesting because it creates a difficulty in managing loads based on incentives, aggregate loads based on incentives. This is something the aggregators might be aware of, should be aware of. And then finally, we evolved the model from shifting to storage and discharge, right? And somehow became surprised. I became surprised about the residual value of V2G. So the residual value from the controllability point of view, very little value. This is also, I think, for me it was a surprise, and because I don't know much about the subject, but the thing is, I think it is also an interesting topic to explore. And then we realize, just to finish, we realize that there is a lot to learn, right? A lot to learn around this subject. Okay, that's it.
Thank you very much, Pedro. I think we learned a lot here. So there is, Dan, you want to handle some questions? Okay, so I think we have, there was a question that I don't see, just sort of showed up on the, was it your question, Pedro? Sorry, Dan, yeah. So it says, if you consider a higher proportion of vehicle to grid, does the linear relation still hold, or it creates as opposite hysteresis?
Okay, so I think the questions are here. I think I can read them, right? Yeah.
That is Dan asking, yeah.
Then, yeah, if you consider a higher proportion of V2G, does the linear relation still holds, or it creates an opportunity set? Yeah, it still holds, because the thing is, here, what I model is V2G is always there, right? But the thing is, once you the opportunity for V2G is only used if you don't have a particle to shift, right? If you have one other user that is available for shifting, you shift it, and it does the same. It has the same effect, right? If you don't have that, if that particular customer is also available for V2G but doesn't have a particle there at the moment, so it creates the particle then, right? So the thing is, everybody is available for here in this model. Every user is available either for V2G or shifting at the same price, right? So yes, so the answer is yes. It does not depend on how many. It will always be linear, the relationship.
Can you likewise incentivize the charging cycle so that there are more particles available later?
Yes. So the thing is, if the idea, the value of V2G is that when you are searching for a particle to move and you don't find, you have to go up in price. And if you have V2G, the particle can be created, because if a user is available to discharge, it immediately discharges, so it creates the same effect now, and then becomes available to shift again, because the charging, it will need to charge and will be able to shift again. So the thing is, what V2G does is gives you the opportunity not to go very high in the prices. So if you have one user that is available for V2G, it will discharge the load, and once the load is discharged, the opportunity to shift the charging that needs to follow the discharge is already there.
So then doesn't the logic follow that a vehicle to grid is only available when the vehicle obviously isn't in use or is plugged in, whereas say a microgrid, which also has a similar battery capability, would be more available more often? And could you apply the same logic and run a model that basically says, instead of vehicle to grid, just say microgrid to grid? And because it has a similar functionality if you aggregate the totality of the capability of the microgrid.
Yes, I would say it is the same, yes.
Okay, Brian, maybe you can tell us why you're asking. Brian is a very important listener for us in the academia. So what is your group trying to do with microgrids?
Well, essentially, you could say we're trying to create that network, a more permanent network of microgrid availability, which then can not only aggregate everything behind the privacy wall, whatever we call that. Some people call it the meter or whatever. that may shift around a bit. But you can aggregate, and then you can make, as you call it, particles more available and more flexible all around, because you have many more resources that can be applied to that, including battery. And actually, some of the modeling on microgrids suggests that the real value of the microgrid continues to increase the more it gets networked into similar arrangements like this. So our long-term goal is to have a grid of grids, essentially each microgrid being its independent capability, but at the same time halonically involved in the grid of grids. And therefore it's available for all these services, and probably reduce the overall economic impact to the utility, but at the same time provides a maximum revenue opportunity to the individual microgrid owner and operator.
So Brian, I will do the intro and we'll follow up, but this is an important discussion to have, because I think what Brian is saying is that this is not just technology specific. This is generalized.
No, yeah,
Right.
Here I try to model it as simple as possible. The thing is, if you an electric car or a water heater, you really have a particle, like a load that is more or less square, right? If you talk in microgrids, I think you have control over the shape of it. So because you have several resources behind that, so it's not just a particle. You can model it as a particle, but it's an approximation that is more rough than for an electric vehicle.
And what the microgrid, I think, allows you to do is to provide the logic complexity at the point of distributed use, as opposed to trying to build that complexity, analytical complexity into the aggregator. You make it more simpler and simpler, as you go along, because within the microgrid you can put logic there that's quite a bit more complex because it's dealing with very known quantities and so on. It's not as in one respect you could say it's more variable than the aggregated whole, but on another way it's more predictable than anything else in the system.
Yes.
Great. I think we'll follow up on that. I think we are exceeding the time, but for people who can stay, Ning Lu from North Carolina State. Ning, we want to ask your own question, please.
Okay, so it's very interesting presentation. I really think this is a new way to do the model.
Yes, I thought it was kind of exploratory. So the thing is, we started that not long ago. So there is, I think, the reason I presented it here to you guys is because I think it's quite new, the view.
Right.
I don't know if it is better than the others. Probably it is not, but I think it is new.
Yes.
Yeah, my main question is about your assumptions, because I think you are using velocity trying to capture the number of particles you have from t to t+1. But I think these in reality has a lot of uncertainties. I listed some of those in the chat box. Mainly, I think you're assuming the aggregator knows the information for how many vehicles are at t, and then how many will arrive on t+1. And then also you have to know the charging duration for each vehicle to be able to how long this token will be available. And then also the user's time to stay, because otherwise you can extend their time, but you cannot extend that long forever, right? So the time they need to charge and then the time they plan to stay will determine your flexibility. So how would you actually incorporate everything into your current model to make it a scalable to large scale systems?
I don't know, Nick. I don't know. So I have some ideas, but I don't have very solid answers for that. The thing is, what I know is that one of the assumptions is that the use is quite small compared to the duration. So the thing is, what we are assuming is that when I take a shower, I discharge my water heater almost immediately compared to the time that I use to heat the water. And I'm also assuming when I translate that to the vehicles that the traveling is quite small compared to the charging of the battery. So we are assuming this is for the maximum flexibility. So for the particles to be able to go ahead until they collide with another one. But we don't have to have that much flexibility. You can constrain that. So the model doesn't need, you don't need to collide with the particle ahead. You can collide with, like, in the space that you can, because when we say that it is constrained ahead in time, it doesn't need to collide to the particle ahead. So you can model it, you can model the shifts to happen only when you have 2 particles ahead, 3 particles ahead. So you have control over that. But the thing is, what we are assuming is that the car is plugged. So you unplug it when you travel from home to office, and then once you get into office, you plug it again. So it's the same car, different place, but from the aggregator. But the aggregator, you are assuming that the aggregator is the same. So you don't change from one place to the other. You don't change the aggregator. So if the car is most of the time plugged, you can control the charging like that, right?
It sounds like there is a lot of food for thinking for younger people.
Yes,
it's fascinating what you are starting, Pedro. I want to go back and maybe just close with this question. Going back to what Brian was talking about, networks of microgrids, you can think about networks of aggregators, things. Mm-hmm. In your formulation, let's say first formulation, the logic for shifting depends on power target. So if you have these networks of aggregators, microgrids, I think it has to be, Pedro, we have written papers on diamonds together. So it has to be interactive. How much target you want to offer in this higher layer, where you have several aggregators or several microgrids, will depend interactively on what your end users can do, and other way around. So there is this another layer of complexity at the higher layer when you have many more. So my question earlier on in the chat was, where does P star come from? It's not an exogenous input if you think about the entire ecosystem.
Yes, exactly.
And I think that is very interesting area also, this interdependence. And so how do you do the interactions so that you take into consideration if you're responding to the price or you're responding to the quantity? I think there are all sorts of open questions. Am I right about that? That P star?
Yes, Maria. I think yes, you are. But my point here is, I'm not really much worried about what P star is, because I just use a ramping up and down triangle. It could be a sinusoidal, it could be a step, like a square wave, whatever. The thing is, it needs to be a wave in the sense that it should be around the average. Otherwise, it's impossible to do, right? So the thing is.
Around the average of the load.
You cannot, the average load. So the expected load. Expected profile. You have a profile, and you cannot just make a step in the profile, because no one can do that. It's impossible to stand. So the thing is, you can do that if you then change, go down and go up. So the capability of the shifting of those kinds of loads is to modulate around the expected load. So you cannot make a step, right? You can a step that is standing. It's impossible to do.
But actually, viewed from electricity markets, if you want these aggregators to participate in US markets, right, in response dynamic pricing and stuff like that, I think that your assumption, sort of formally speaking, is that aggregators are price takers. They don't affect.
Yes.
Now, we have written even papers on the distribution network, if you remember, how these aggregators can help with congestion of the grid. Like people are very concerned about clusters of electric vehicles creating congestion and needing new transformers, and with microgrids the same way. So if you go one level higher on how are these exogenous prices or amounts of power affected, how are they interacting with the
my concern, Maria, is that the aggregator needs to know what he can do.
And so that's why it's interactive, both.
Yeah, exactly.
Both.
But whatever he wants to do, he has to be able to do it. And I think the most important point of my talk is that there are some things you can do and some things you cannot, right, no matter what the price is. So there are intrinsic limitations for the load regulation based on shifting. So those you cannot, you have to live with those. And so you can ramp very quickly. Yes, you can, and you can stand for some time. Yes, you can, but there is a relationship between the magnitude of the change and the frequency of change, and this is intrinsic of it's
yeah. So let me close. Really, thank you. This is a lot of food for thinking. But I want to say also that at the higher layer, at least in the US, now there is a very big push. I have a phone call tomorrow. Let's say FERC wants to really pursue what's known as bid in demand, right? Rather than just have one-sided generation market. And all these technologies that we are talking about, they lend themselves to doing this. Now the independent system operators are very opposed to the idea of bid in demand, because they cannot, quotation, trust what the aggregators at demand can do. So exactly. I think you are addressing this real important question. What is, I've been insisting, and we have interacted again for years now on Diamonds. I've been insisting that when you bid in the market, your bid is implementable physically. And it's come now to real problem with bid in demand, because you bid something and the ISO can not counts on that, but actually is not physically implementable. So I think that your talk is one of the first ones on the demand side that actually addresses what can aggregator do given the logic at which it schedules its members, and depending on the part that I think Lou was asking is that really depends on technology. You can move or not, and it depends on heterogeneity. So I think this is engaging into a real important area that's underestimated, and it has implications on a lot of stuff. And Rupa is still on the phone, and she'll tell you, okay, are you going to create instabilities to my system if you do this? To true physical dynamics and so forth. So I'm so glad that you are doing that and that you shared with us. Thank you very much.
Maria,
Maria,
I just